All right, so let's talk about angular momentum in systems. And we're gonna go back to my kid being on that merry-go-round one more time. If you don't remember, down at Balboa Park, they have this big dish-shaped thing that kids can sit in, and then from the outside you can spin it, and they go around and around and around. And the faster you spin it, the more they feel like they're getting pushed backwards, and good times, yada yada. But let's talk about that. Let's imagine that I've got it going at a good speed. It's going to be perfect, so there's no friction going on. Ethan is now just spinning for the rest of his life until his dad takes pity and stops it. But what Ethan can do is he can lean forward and he can lean back. And I already talked about how if he leans forward, that would cause the rotational inertia to decrease because now the mass, I'll do this in a separate color, because now the mass is slightly closer towards the center, which means the mass is less, the closer the mass is to the center, the less rotational inertia there is. So as he leans forward, rotational inertia decreases, and that causes the angular momentum of the entire thing to increase, or the angular velocity to increase because of this idea of conservation of angular momentum. So we've already talked about that, but I want to break it down into some separate pieces and notice what's happening here. So the angular momentum for the entire system, L system, has always been the same. The change in it was zero. But let's look at the individual pieces and talk about what happened there. So I'm going to look at the change in the angular momentum of Ethan, and I want to go look at the change in angular momentum of the merry-go-round itself. So for Ethan, when Ethan leans forward, his rotational inertia is going to decrease. So this decreases. And while the angular velocity of, well, let's pause that for a sec. Let's look at the merry-go-round. The merry-go-round, when Ethan leans forward, its rotational inertia does not change at all. So that's interesting because we know something else about it does change. When Ethan leans forward, it starts spinning faster. So the rotational inertia of the part of the system was not conserved here because now the merry-go-round actually has more angular momentum than it did before. So if this thing now has more angular momentum, then the only possible thing to conclude here is that if the whole system had no change in angular momentum, then Ethan must have actually had a decrease in angular momentum. So he does speed up by a little bit. He still goes faster because he has to be going the same speed that the merry-go-round itself is going, but his increase in angular momentum is not as great as, like if the rotational inertia dropped by a factor of 2, so it was like 1/2 what it was before, his rotational inertia maybe only went up by 1.2 or something like that. So it doesn't exactly cancel out. He's going faster, but not enough faster. So within this system, we can see that we had let's say a negative change in Ethan's angular momentum and a positive change in the merry-go-round's momentum and a 0 net change in the entire system. But now what's important to mention here is if we're looking at the individual pieces, that means that there must have been a torque applied to each one of them. And the reason why we know that is the only way to change angular momentum is by applying a torque over time. If we want a delta L, we need a torque applied over time. So if we had a change here in Ethan's angular momentum, then he must have had some kind of torque applied over a period of time. But this is a little bit confusing, and they do make it easy on AP exams to get this question wrong. Because trying to figure out where the torque exists is a little bit more challenging. So let's talk about what would actually happen if Ethan threw a ball across this merry-go-round. So Ethan's moving in circles, and if Ethan threw a ball straight across, relative to his own motion, he could not throw like if somebody was on the other side, his brother, he couldn't throw the ball straight across to him, because if he threw the ball straight across, Shelton, his older brother, would already have moved, and by the time that the ball actually got to the opposite side, uh, Shelton's going to be way over here. And like, if anything, Ethan could probably, if you're spinning fast enough, have an easier time throwing the ball to himself than he would having throwing it to his brother. If he wanted to throw it in what seems like a straight line to him, he actually has to throw it this direction, not to where his brother is at the moment that he's throwing, but to where his brother will be. Well, the same thing applies if he's leaning forward. To actually lean forward, he's not actually going towards the center. He actually has to go off center, leaning into the direction of motion that's happening here. So when he does that, when Ethan leans forward or whatever on this ride, he's actually going to be applying a torque that is in, or a force that's in this direction. And how much of an angle that is depends on how fast he's spinning. But when he does that, that means that he's actually applying a little bit of a torque onto the object, which causes it to rotate faster. And if he's applying a torque to the system or the merry-go-round is applying a torque to him, which decreases his angular momentum and increases the angular momentum of the merry-go-round. So the big takeaways, and I'm sorry if this has been confusing at all, is that angular momentum is conserved within systems, but within individual parts of the system, that isn't necessarily true, and almost definitely isn't true if something within the system is changing. So if we have a system that the angular momentum is constant, we can still have a decrease and increase in individual parts. But then the other takeaway is if we do have a change in angular momentum, we must have a torque applied. And it's generally good enough for you guys that if you recognize that there's a change in angular momentum, you can say, I know a torque was applied. You don't even necessarily have to say you know where it came from, but you say it must have been applied because I can see that there was a change in angular momentum of this particular part of the system. So there we go. Thank you guys for watching.